Good afternoon, all of you. I am Bandana Kumari, Assistant Professor in Department of Information Technology, IIMT College of Engineering, Greater Noida. I am going to deliver lecture on topic deadlock. These are the outlines of deadlock. First of all, I will define deadlock. Then I will explain about examples of deadlock, describe about system model and what are the necessary conditions of deadlock, and I will explain the source allocation graph. Then I will explain about deadlock prevention, deadlock avoidance, and Banker's algorithm. Deadlock is a set of situations. Deadlock is a situations where each and every process are blocked because each process holding a resources and waiting for another resource that is held by another waiting process. That is called deadlock. For example, two trains moving towards each other and no will further proceed until other has gone. In a multi-programming environment, several processes may compete for a finite number of resources. A process requires resources. If the resources are not available at that time, the process enters a waiting process state. Sometimes a waiting process is never again able to change state because the resources it has requested are held by other waiting process. This situation is called a deadlock. Here, there is an example of deadlock, traffic only in one direction. Each section of a bridge can be viewed as a resource. If a deadlock occurs, it can be resolved if one car backs up, trimmed resources and roll back. Several cars may have to be backed up if a deadlock occurs. It means a starvation is possible. It means possible. Resources types R1, R2, so on Rm. CPU cycles, memory spaces, input-output devices, each resources type Ri as Wi instances. Each process utilizes the resources as follows: request, use, and release. Deadlock can arise if four conditions hold simultaneously. These are the four necessary conditions. If these conditions hold simultaneously, then deadlock will occur. Mutual exclusion, only one process at a time can use the resources. Hold and wait, a process holding at least one resources is waiting to acquire additional resources held by other process. No preemption, a resources can be released only voluntarily by the process holding it and after that process has completed its task. And last one is circular wait. There exists a set of process like P0, P1 and so on Pn. P0 holding a resources and waiting for another resources that is held by P1 and P1 holding a resource and waiting for another resources that is held by P2 and so on Pn with holding a resources and waiting for another resources that is held by P0. These are the resource allocation graph. A set of vertices V and set of edges E. V is partitioned into two types. It means vertices are partitioned into two types. Set of vertices P. It means P consists of all process in the system and R set of consisting of all resources types in the system. In this graph, we can see that P1, P2, P3 are the process, and process is denoted by the circle and resource is denoted by the rectangle. And dotted is represented in a stance of resource. It means R2 is a resources and dotted represent the instance of resource R2. Assignment is and directed is RJ request to assigned resource instance of J assigned to PI. P1 is a process and that request instance of RJ. Pictorially, we represent each process P as a circle and each resource type Rj as a rectangle. Since resource type Ri may have more than one instance, we represent each such instance as a dot within the rectangle. Note that a rectangle is points to only the rectangle R1, whereas an assignment is must also designate one of the dots in the rectangle. In this graph, we can see that cycle exists in this graph. R3, P3, R2, P2. P2 holding an instance of R2 and waiting for another resources that is held by P3, and P3 holding a resource of R3 and waiting for another resources that is held by P2. In this graph, we can see that cycle will exist in this graph. Minimize. Resource allocation graph with the deadlock. It means there is cycle exists in this graph and deadlock will occur. Resource allocation graph with the cycle but no deadlock. In this graph, we can see that P1, P3, P4, P2. These are the process and P1 holding an instance of resources R2 and waiting for another resources that is held by P2 and P3. We can see that there is cycle P1, R1, P3, R2. If P4 release an instance of R2, then cycle will break. So we can say that the resource allocation graph with the cycle but no deadlock. If graph contains no cycle, no deadlock. If graph contains a cycle, it means if only one instance per resources type, then deadlock. If several instances per resources type, possibility of deadlock. Now I will explain about deadlock preventions. Deadlock prevention provides a set of methods for ensuring that at least one of the necessary conditions cannot hold. These methods prevent deadlocks by constraining how requests for resource can be made. First one is mutual exclusion. In mutual exclusion, in order to break this condition, resource should be held in shareable mode. Example of the non-shareable resource, a printer cannot be simultaneously shared by several processes. Shareable resources, in contrast, do not require mutually exclusive access and thus cannot be involved in a deadlock. Only one read-only files are a good example of shareable resources where set of process can read only files. Second one is hold and wait. Hold and wait must guarantee that whenever a process requests a resources, it does not hold any other resources. requires process to request and be allocated all its resources before it begins executions, or allow process to request resources only when the process has none. It means in this case, in these conditions, low resource utilizations and it may be starvation possible. Third one is no preemption. If a process that is holding some resources request another resources that cannot be immediately allocated to it, then all resources currently being held are released. Preempted resources are added to the list of resources for which the process is waiting. Process will be restarted only when it can regain its old resources as well as the new ones that it is requesting. It means that the no preemption means uh, resource cannot be released by the process, but in that case, deadlock preventions that process release the resources for the process. No preemption. Alternatively, if a process requests some resources, we first check whether they are available. If they are, we allocate them. It means if resources are available, then allocate to that process. If they are not, we check whether they are allocated to some other process that is waiting for additional resources. If so, we preempt the desired resources from the waiting process and allocate them to the requesting process. If the resources are neither available nor held by a waiting process, the requesting process must wait for the instance of resources. Last one is circular wait. The fourth and final condition for deadlock is the circular wait condition. One way to ensure that this condition never holds is to impose a total ordering of all resources types and to require that each process requests resources in an increasing order of enumeration. To illustrate, we let R1 equal to R1, R2, so on Rm are the set of resources types. We assign to each resources type a unique integer number which allows us to compare two resources and to determine whether one precedes another in our ordering. Formally, we define a one-to-one functions. For example, if the set of resources type R includes step drivers, disk drivers, drives, and printers, then the function f might be defined as follows: f step driver assigned 1 and f disk drive 5 and printer 12. Each process can request resource only in an increasing order of enumeration. That is, process can initially request any number of instances of a resource type, say R. After that, the process can request instances of resources type Rj if and only if Rj greater than Fr. Now I will explain about deadlock avoidance. Deadlock avoidance means requires that the system has some additional or prior information available. Simplest, the most useful model requires that each process declare the maximum number of resources of each type that it may need in the futures. It means operating system has prior information process which process uh, declare the maximum number of resources. The deadlock avoidance algorithm dynamically examines the resource allocation state of ensure that there can be never be a circular wait conditions. Resource allocation state is defined by the number of available and allocated resource and the maximum demands of the processes. Required that the system has some additional prior information available. The process, which process request for a resources in the futures. Simplest and most useful model requires that each process declare the maximum number of resources of each type that it may need. Resource allocation state is defined by the number of available and allocated resources and the maximum demands of the process. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. System is in safe state if there exists a safe sequence of all process. Sequence P1, P2, P3 and so on Pn is safe if for each Pi the resource that Pi can still request can be satisfied by currently available resource held by all the Pj with j less than equal to I. If Pi resources needs are not immediately available, then Pi can wait until all Pj have finished. When Pj is finished, Pi can obtain needed resources, execute, return allocated resources and terminate. When Pi terminates, Pi plus 1 can obtain its needed resources and so on. Deadlock avoidance. If a system is in safe state, it means no deadlock. And if system is in unsafe state, possibility of deadlock, it means it may be deadlock or not. Avoidance ensures that a system will never enter an unsafe state. In this picture, we can say that safe, unsafe, and deadlock state. Deadlock represented by a rectangle, it means system is unsafe state. Resource allocation graph. In this graph, I will explain about claim is Pi, P1, Pi tends to Rj. It means P1 request for an instance of R2 and age is represented by dot and that age is called claim age, dash line. Rj indicated that process Pj may request process J, Rj represented by a dashed line. Claim is convert to a request is when a process requests a resources. When a resource is released by a process, assignment age is convert to a claim age. Resource must be claimed priorly in the system. In this graph, you can say that the P1 request a resource instance of resource R2. If R2 allocate the instance to process P1, so that age is called assignment age. In this graph, unsafe state in resource allocation graph, because we can see that there is a cycle exists in this graph. It means unsafe system is in unsafe state. Now I will explain about Banker's algorithm. The Banker's algorithm is a deadlock avoidance algorithm that tests for safety by simulating the allocation for predetermined maximum possible instance of all resources, then makes an safe state. Check to test for possible activities before deciding whether allocation should be allowed to continue. Banker's algorithm is used for deadlock avoidance. When a new process enters the system, it must declare the maximum number of instances of each resources type that it may need. This number may not exceed the total number of resources in the system. When a user requests a set of resources, the system must determine whether the allocation of these resources will leave the system in a safe state. If it will, the resources are allocated. Otherwise, the process must wait until some other process releases enough resources. These are the four data structure of Banker's algorithm: available, max, need, and allocations. Let n is your number of process and m is a number of resources types. Available is equal to vector of length m and available j is equal to k. There are k instance of resources type rj available, and max n cross m matrix means if may I max ij means equal to k, then process pi may request at most k instance of resource type rj. Allocation matrix n cross m matrix allocation ij is equal to k, then pi is currently allocated k instance of rj. Need n cross m matrix, if need ij equal to k, then pi may need k more than instance of rj to complete its task. And we are calculating need is equal to max minus allocations. Need I and j and max I or j minus allocation ij. Safety algorithm. Safety algorithm is used to find whether a system is in safe or not. Let first and finish be vector of length m and n. Find an index I such that both finish and need work is equal to work plus allocations, and if finish I is equal to true for all I, then the system is in safe state. If work equal to available, to finish I equal to false for I 1 3 tends to n. Find an index I such that both finish I is equal to false and need less than equal to work. If no such I exists, go to step 4. Work is equal to work plus allocations and finish I is equal to true. Go to step 2. If finish I is equal to true for all I, then the system is in safe state. Resource request algorithm for process. Resource request algorithm is used to find whether a request of process will satisfied or not. Request is equal to request vector process pi. If request equal to k, then process pi wants k instance of resources type rj. If request less than equal to need, go to step 2. Otherwise raise error condition since process has exceeded its maximum claim. If request less than equal to available, go to step 3. Otherwise, PI must wait since resources are not available. Pretend to allocate requested resources to PI by modifying the state as follows. Available is equal to available minus request. Allocation is equal to allocation plus request. And need is equal to need minus request. If safe, it means the resources are allocated to PY. When process requests for an instance of resources, if they allocated, then system will save. If unsafe, it means process must wait and old resource allocation state is restored. Examples of Pelker's algorithm. 5 process P0 through P4 and 3 resources type A and 10 instances. 5B, 5 instances, and C, 7 instances. Snapshot at that time, P0. Here, P0, P1, P2, P3, P4. These are the process, and they are assigned these resources, allocation, max available. These are the metrics of Banker's algorithm, and we can say that data structures of Banker's algorithm. So first of all, we will find need. The content of the matrix need is defined to be max minus allocation need. A, B, C, P0 743, P1 122, P2 600, P3 011, P4 431. The system is in safe state since the sequence P1, P3, P4, P2, P0 satisfies safety criteria. Examples of algorithm to be continued. Step 1, for first of all we check at P0, need less than equal to available 743 less than equal to 332. Condition is false. We can see that 743 is greater than 332 and available resources is 332. So we examine another process P1. Step 2, it means we will check at the process P1. Need less than equal to available 122 less than equal to 332. Then there is condition true. New available is equal to available plus allocation. It means now available is equal to 532. Similarly, we examine another process P2. Step 3, for process P2, P2 need less than equal to available. These are the conditions. 600 less than equal to 532. 600 is greater than 532. It means condition is false. Similarly, we examine another process because here condition is false. So I will go for another process P3. Step 4, for process P3, P3 need less than equal to available. These are the conditions. 011 less than equal to 532. Yes, condition is true. New available resource is equal to available plus allocation. So new available equal to 743. Similarly, we examining another process P4. Step 5, for process P4, P4 need less than equal to available 431 less than equal to 45743. Condition is true. We can see that 431 is less than equal to 743. It means condition is true. The new available resource is equal to available plus the allocation. It means 745 is available resources. Now we again examine each type of resource request for process P0 and P2. Step 6, for resources P0. P0 need less than equal to available 743 less than equal to 745. Condition is true. New available resources is equal to available plus allocation 755. Step 7, for process P2. P2 need less than equal to available. We will check 600 less than equal to 755. Condition is true. New available resources is equal to available plus allocation. It means 755 plus 302 equal to and greater than 75 and 7. Hence, we execute the banker's algorithm to find the safe state and the safe sequence like P1, P3, P4, P0 and P2. These are the references